Please.
Okay. Okay, great. So thanks a lot, Katya, for the very kind invitation, and I'm very happy to give this talk. And thank you everybody who is uh, attending online. So as I said, I'm not very used to online talks. It's not really my thing. But at the same time, it's kind of nice to know that I can talk and communicate with people who are even in other continents. So I'm going to talk about some works which are based works with Lauri Oksanen from the University of Helsinki, and it's about some stability questions, and it's an inverse problem for the wave equation. And the main thing about this inverse problem is that the qualitative question, the uniqueness problem, can be solved essentially right now with only one technique, which is one of the main techniques in the field, the boundary control method. So these works in a way investigate how one can prove stability for the for, via the boundary control method. And uh, I will show an abstract result about the stability problem. And as we will see, it is connected to a quantity coming from control theory. And then I will, in the second part of the talk, depending on how much time we have, I will say a few words about how one can study this quantity, which is related to control theory, and obtain some results about it. So the problem is the following: is just a wave equation with a flat Laplacian in Euclidean space, and we have a potential, which is it's the potential that we want to recover. And so we will suppose that we have a compact K in which we want to recover the values of our potential, and we have our observation set omega, and this allows to define a so-called source to solution map, which is a variant of the Dirichlet to Neumann map, but here there is no boundary. So yeah, I mean the physical question is that we use some sources f. The sources are supported in our observation set omega. We get some resulting waves, and we can only observe these waves in the cylinder 0t times omega. And we want to use these measurements in order to recover our potential in a compact set. So mathematically speaking, we define the source to solution map. To a source f, this associates the solution, the restricted in the cylinder 0t times omega. And of course, uh, the first question is, can we recover the potential in a compact? So the answer is yes. So as we will see, this can be done by the boundary control method. And if one can recover the potential, then the next natural question is, can we prove a stability estimate? So stability estimate is an estimate that bounds the difference of the potential in some appropriate norm by a modulus of continuity applied to some norm for the difference of the source to solution maps. So as I said, the the main point about this problem, so it is kind of a, one could even see it as a model problem, because the geometry is uh, in a way it's just the Euclidean space, but it's already uh, kind of um, kind of interesting to and not trivial to prove uniqueness. So the point is that here, essentially, the only way to attack this problem, I mean, right now, the only technique that we have is boundary control method. And essentially, one of the other really, let's say, for the similar problem, or for the Dirichlet to Neumann map, another main approach is based on geometric optic solution and recovery of the geodesic ray transform, light ray transform, I mean different versions depending on the time dependence, and then inversion of this transform. But here, the general principle is that if you want this method to work, then the domain where you have the data, the domain that you have your measurements, in a way has to surround the domain that you want to recover. So there is some kind of geometric uh, assumption that needs to be in the problem. And the difficulty in this problem that we look, even if it's just on the Euclidean space, is that there is no correlation whatsoever about the compact K, where we want to recover the potential, and the set omega, where we observe. So that's the difficulty. And this is where boundary control method is really powerful. And yeah, this is the point I want to make, that this is a problem, let's say a model problem, for which right now we can only solve using the boundary control method. So, of course, as you may guess, proving a stability estimate means even more estimates than usual. So I will try to focus on the ideas of the boundary control method in the way that we use it in order to prove our stability estimates. So essentially, I will present some the key ideas of the boundary control method. So the first important point is that boundary control method is based on two fundamental properties of the wave equation, which are finite speed of propagation and unique continuation. So finite speed of propagation, I'm not going to detail on that. It's essentially energy estimates for the wave equation. It's what gives well-posedness for the wave equation when the data are on a space like a hypersurface. And yeah, it's just energy estimates, and it's essentially the proof the same for any dimension. The unique continuation is a different property, a different problem, and it asks essentially, let's suppose we have a solution of the wave equation. Let's suppose that our solution vanishes in some domain. Which is the maximal domain in which our solution has to vanish? In other ways, if we have some vanishing property for the solution, how much can we propagate uniqueness? The optimal result for the wave equation I considered in the beginning of the equation is that in a picture is that if your solution equation is zero on this blue cylinder, so I mean in the picture is a rectangle, but in more dimension you can imagine a cylinder, then it has to vanish on on this larger diamond that I have here in yellow. And the important point about this result is that energy estimates still allow to propagate uniqueness. So they are kind of related in a way, but they propagate uniqueness in a space-like direction. So this would be in this direction. But here the main point is that this allows to propagate uniqueness in time-like directions. And this result that I'm showing, even for this wave equation with a potential, flat Laplacian plus potential, was in fact proved in the end of 90s by Tataru. And then slightly, I mean, there were generalizations in many different contexts by Tataru, Robiano, Hermander, Julie. But the point is that this unique continuation property is a much more subtle and deep property, and I mean difficult to show property than finite speed of propagation, which is just energy estimates. Now the interesting fact, and this is what makes the link with control theory, is that by duality, so this is an abstract functional analysis argument, one can show that this unique continuation property is really equivalent to what we call approximate controllability property. And a way to say what is approximate controllability is that you look at the set UFS. So these are, I recall, solutions of the wave equation with source F that we consider at time S. So by finite speed of propagation, this is a subset of L2 of M omega S. So what is M omega S? Is the domain of influence of the open omega at time S. So this is finite speed of propagation, the fact that UF at time S is contained in this set. But unique continuation says that not only is the set contained in L2 M omega S, but it's in fact dense in it. And what does it mean, controllability? It means that can I find sources so that my solution takes some prescribed value, attains some prescribed target. Approximate controllability says that you cannot attain your target, but you can be as close as you want to the target. So this is what approximate controllability means. And this is just an abstract functional analysis thing that gives that. It's not. This is how it's going to be used in the boundary control method. So let's start with the first part, which is in the literature is called sometimes Blagovenzenski identity, which is a very clever way. I mean, the proof of this is very simple. It's 2 lines, but one still has to think of the idea. So what is the property we're talking about is the fact that if we have the same source to solution maps, then we recover these inner products. So I recall FH are arbitrary sources, T prime arbitrary times, and these inner products here, they are inner products in space. Once you fix time, UFT, U2F, etc., they are just functions on space. And I recall again that U1, U2 are 2 different solutions, one associated to potential Q1, the other associated to potential Q2. So here, this is something one needs to observe. It has been done quite a few years back, but still, it's quite a. I find it quite a beautiful because the proof is that you consider this capital W. So this is a function that depends on 2 variables, and which is the function that T prime associates these inner products. And then you apply the 1D wave operator on W, and you realize that this it depends only on the source solution map. So of course, if the source solution maps are the same by well-posedness of the wave equation, then this inner product will also be the same. So the proof is simple, but yet one has to think applying the 1D wave operator to this thing. So I always find it quite amusing, this property. So, okay, this is recovery of the inner product. And now let's try to give some intuition. If you have recovered the inner products, then what is the inner product? It's an integral. So in fact, what you would like to do is to start localizing your inner products. So why? Because the idea is that if you have an integral and then you are able to start localizing more and more the set on which you integrate, you can hope, you can expect, I mean, if you have enough regularity, but in fact, you don't even need so much regularity, that from an integral equality, from an integral identity, you can go to a point value. Why? Because it is just differentiating the integral in a way. Or if you have less regularities, you can think in terms of Lebesgue differentiation theorem.
Spyridon, may I interrupt you for a minute?
Of course, of course.
Question for you. So
Yes.
this actually proves this is more towards uniqueness rather than recovery, right? You have not quite shown that you can recover the inner product. You've shown equality of inner products. It's more like uniqueness, not reconstruction. Am I correct?
Yes, yes, yes. I mean, up to now, and like in these parts, I'm only talking about uniqueness. So if the source solution maps are the same, then these inner products are the same. And of course, but the way I present those steps is the next. I mean, what we actually do is that we prove a quantitative version for each of those steps. But of course, for instance, I was going to say that later, but for instance, this step is a step that is particularly easy to quantify because what is the proof of this step? You realize that you apply the wave operator to these inner products, and this depends only on lambda. But then you can have an energy estimate for the wave equation just in 1D, and this will automatically give you a very good stability because it's just the stability of the source and the solution. So yeah, exactly. No, as I said, this will mainly focus on the qualitative steps, but in the way that we implement them so that they can be quantified. Exactly.
Okay, thank you.
Yeah, exactly. So for instance, yeah, we can already think in terms of quantitative estimates. This step is easy to quantify because it's energy estimate for the wave equation, and in fact, this step alone it sleeps it stable. Exactly. I mean, this is where the least stable part is going to come. And yeah, once again, I'm just thinking in terms of qualitative problems. It means, recovery, just recovery. And yeah, I'm trying to motivate where approximate control comes. So at this point, we have information about, we have recovered the inner product. In the quantitative context, we can think that we have a good estimate for the difference of those inner products. We have a good bound between the difference of these inner products and the difference of the solution maps in the, let's say, L2 to L2 norm. And now we want to start localizing our inner products. And this is exactly where it's kind of natural that you want to control your solution, because you have here we have F and H are arbitrary sources. So we have this degree of freedom that we can choose our sources. So of course, if I can choose one of those sources in a way that my solution starts localizing somewhere, then in fact I'm almost done, because at least for recovering the two different solutions. Because if I can just take a wave and choose a source such that my wave becomes a characteristic set, this integral will be an integral on a characteristic set, and then I can hope to make it smaller and smaller. And we know by approximate control that we can almost do that, so that's already good. But now there is a tricky part, is that, okay, approximate control can give me, let's say, some g, such that UG at time t is close to this target here. So what is this target? Is solution with source f for some arbitrary f. And the main point is that if I choose my control g supported in this time interval, so you can think just that my control g has s supporting time in total, because it's from t minus s to t. Then the main point is that this guy here, by finite speed of propagation, in any ways, it will be supported in this domain of influence. So just you choose your control appropriately so that by finite speed of propagation, it will be supported in some domain of influence. So a fortiori, this is going to give us a characteristic set in a domain of influence. And this, we can do it. We can find an approximate control. But the problem is that, okay, we can do this, let's say, for one solution, U1, but then nothing guarantees that the same approximate control is going to work both for U1 and U2. Because, okay, we can find a source H that is going to force our solution with potential Q1 to be close to this target, but there is no reason that the same source H will also work for the other solution U2. So now this is where that's quite clever. How one can use approximate controllability again to prove that in fact this is possible. So there is this key identity here. This key identity will become very important and maybe later in the discussion, but I will just say that, okay, this is just finite speed of propagation that creates this orthogonality. You can put this domain of influence, and you can see that you have these two pieces. This is supported outside of the domain of influence, and this is supported inside of the domain of influence. So these two are orthogonal. And this uses that by finite propagation, we have the support property. Now, recall that the inner products are the same. We have recovered the inner products. So if you have U1 and U2 to different solutions, the left-hand side is going to be the same because this norm squared is just an inner product. So that means that these two quantities, this orthogonal decomposition is going to be the same as well for the two functions U1 and U2. And now it's the clever part is to remark that in fact, I can just take infimum over G supported in this cylinder. And the key part is that this quantity here is independent of G. And since by approximate controllability, I can be as close as I want to any target in here, when I take the infimum over G of this quantity, it's going to be just this positive thing, which is independent of G. And if I take infimum for the right-hand side, the same thing is going to happen. And these two are equal, so the infimum have to be equal as well. So the infimum have to be equal, but then you can go.
Spyridon, excuse me. Could you please return to the previous slide, to the previous slide?
Yes, this one?
Yes. And the fourth item is problem. Need to show that the same G was for U1 and U2. What is need to show? I'm afraid it is just not correct. If you have different potentials, and then to hope that the same G approximated the waves for one potential and another potential is hopeless. No, maybe I understand nothing, but could you please comment it?
You're absolutely right. So the only reason this works is because in this part of the problem, we are working under the assumption that the source to solution maps are the same. So this is not.
You assume that lambda1 equals to lambda2.
Exactly. So gradually we are working under this assumption, and of course, this is totally hopeless to work for arbitrary potentials. But in fact, by using the information that the source solution maps are the same, what we show is that the same approximate control can work.
Thank you. Excuse me.
Thank you.
Okay.
No, that's a very good point. Exactly. So this really uses, and the way you can use it in the mini proof I saw, because of course it's a little fast, is because we use the fact that the inner products are the same, and we use it here. And the fact that the inner products are the same is a consequence of the fact that the source to solution maps are assumed to be equal. Exactly. So this is a very clever way using again approximate controllability to show that in fact you can have the same approximate control. And I mean, okay, there's no reason to give more details. Once you have this, you can go back to this equation and you can use this property. And the important point is that we had already that the inner products are the same, just for sources G, F, or FH, as I write. But now, using this thing, this decomposition, this orthogonal decomposition, and the fact that you can have the same approximate control. So this is a consequence of this equality, because it says that in fact, if you have a good control for U1, it's also going to be a good control for U2, because if U1G is close to this target, then the same G, U2G, is going to be close to this target. So this is the key identity that we get by approximate controllability, always under the assumption that the source solution maps are the same. And then using this, we can indeed incorporate characteristic sets in our inner product. And now, as I said, once we can have a characteristic set in our inner product, we can use it to localize, because S is a free parameter essentially. So since S is a free parameter, we have an inner product here, but this inner product we can localize it. And indeed, from an inner product, we go to a point value. So just to see, because I think, you know, it's a very beautiful method, and essentially I'm explaining boundary control method from the point of view of our work with Lauri, because I'm not giving all the quantitative estimates. But I think it's still nice, and in a way, you can see exactly here the power of boundary control method is that this parameter S is a free parameter. You can use it to create domains of influence. So you can imagine you have your set here, omega. So this is the boundary of omega. You zoom a lot, so it's straight. And now you can just use domains of influence that you send, and you can also repeat the argument and take intersection of domains of influence. And you can just use them so that you localize in any point. And here you see the power of boundary control method, because you can do this in any geometry. In fact, you just recover point-wise. You use an arbitrary point in the manifold, because this works exactly the same way in a Riemannian manifold. And by just sending some domains of influence, you localize close to a point. And then indeed you recover point value equality. And once you have this, then you just need to say that you can find the source H that is close, that localizes close to a line. So this is classic geometric optic solutions. Then you will get that the two solutions are the same, and then it's just an algebraic game. I mean, algebraic manipulation to go back from the solutions to the potentials. So I'm not going to detail too much on that. Yes, this is just the geometric optic solutions that you use. I will just, I mean, I still need to say a few words about the stability. So the main point is here, when we recover the inner products, but localized in domains of influence, is that the key quantity that we need to make this quantitative. So you have this quantity here, and you have three parameters. I mean, you have essentially two. You have this epsilon, you have this constant that I'm going to talk about, and you have this alpha. So what is epsilon? Epsilon is exactly the precision of the control. So it makes sense that you need to quantify how much close you are to the target. So this is the precision of the control. But it turns out that what is really important when you want to quantify each of those steps is that you need to know how violent your control explodes. And this is exactly what in control theory you call the cost of the control, or of course here I should be careful, it's the cost of the approximate control. I mean, because this is not an exact control, but you know, let's call it just the cost of the control here. So this is the cost of the control. So it says, okay, you have an approximate control. For every epsilon, you will be epsilon close to your target. But of course, you expect that this control, as epsilon goes to zero, its norm is going to explode. And what is alpha here? Alpha is, as I said, this key identity comes from the fact that you use an infimum. This infimum is, we talked about the infimum of this quantity, which is for which we use approximate controllability. And this infimum is in general not attained, and we regularize this problem. And once we regularize using this parameter alpha, and then we have indeed the minimum that we need to use appropriately. So this is the alpha. It's a free parameter that is related to regularizing this minimization problem. And I'm just going to make a comment which is important. I mean, interesting, is that saying that there is a minimum of this quantity for alpha equal to 0, it means that, what does it mean? It means that, in fact, the approximate control is not only an approximate control, but it is an exact control. It means that in fact one can take epsilon equal to 0. This would mean that you can minimize this problem for alpha equal to 0. But for the wave equation, there is a necessary and sufficient condition for exact controllability, which is the famous geometric control condition. And this is essentially never satisfied in our case, in the domain where we apply this for domains of influence. So it's really a problem that we have to minimize. So yes, that's the main point. You have to very carefully take each of those steps, quantify, and the key quantity that appears is there's this interplay between precision of the control, cost of the control, and regularization. So this is what gives this abstract result, which says that if the difference of the source solution maps is smaller than this guy here, then the potentials are epsilon close. Of course, you need some time t large enough. This is expected, and you also need some a priori assumption of the potential. So of course now the question is, okay, this is some kind of stability. This is a quantitative estimate, but what is the stability? What is? And the answer is, well, we don't know, because of course you see that this is a stability that uses this abstract constant, which is the cost of the approximate control. So it's not a logarithmic stability, it's not log-log, it's just an abstract result, but it's a result that makes the link and says that once you know you have some bound on your cost of the approximate control, this is in a way the quantity that will give you that information about the stability of your problem based on the boundary control method. So I'm going to say a few words about, okay, of course this motivates the question, okay, do we have any information about this quantity, this A here, the cost of the approximate control? And so I will say a few words about it, and yes. I already said that unique continuation by duality is equivalent to the property of approximate controllability. And as it turns out, so this was proven by Obiano, a quantitative unique continuation result will give exactly information about the cost of the approximate control. So what we just saw motivates the study of the problem of quantitative unique continuation. So what do we know about it? So for the wave equation in 2015, there are independent works by Bossi, Kirilev, Lassas, and Laurent Leoto that prove quantitative estimates for the wave in slightly different contexts. So in the work by Laurent Leoto, it's optimal stability, and they quantify the more general theorem. In the Bossi-Kirilev-Lassas work, they have some more explicit dependence, and there are some. So there are some differences, and in this in our work with Lauri, we focused on the let's say on the results by Laurent Leoto, in which they prove optimal stability for the wave equation, at least in the case of I mean, in a even more general case than the one we're looking for, but in particular for wave equation in Riemannian manifold with potential Q. So let's see how a quantitative unique continuation result looks like. So we have a solution, we have a time t large enough, and here we control the norm of our solution in the whole space, so M is the whole manifold, by some constant. Here we have the norm in the whole space, so this is why these estimates are so-called conditional estimates. And the main point is that here we have the observation that we do from a cylinder omega at time minus t. So
excuse me, what is L capital M omega? T greater
yes.
than, what is that?
Exactly.
L.
Yeah. So this is we're going to talk about it. So here I just said there is some minimal time. So we can say that this is a minimal time. Why? Because for the wave equation you need minimal time for unique continuation.
How is it connected with geometry? What is the
Exactly.
meaning of this?
Exactly. So the minimal time here, it's exactly the greatest distance between omega and m. So we take the supremum of the distances of omega and a point in the manifold m. And this is really the minimal time for which you can have unique continuation by finite speed of propagation. I will talk about it because this is really the important thing here. So yes, this is the minimal time given by finite speed of propagation. This is related to the distance between omega and m. I mean, omega is inside m, but I mean, it's exactly the greatest distance that a point in omega can have from a point in m. So
Is
this is
it,
essentially
is it equal to time, to the time which is required for the solutions for waves to fill all the manifold M, something like this?
exactly. We can think of it like this. It's the time essentially given by finite speed of propagation, in the sense that if t is smaller than this, then finite speed of propagation will be violated. But the point, yes. So the point is that there is a minimal time, which is exactly what you would expect. We can also state it exactly as you said. And this is a quantitative estimate. And yeah, so just to say, for those who see this for the first time, if you imagine that indeed your solution U is 0 in time omega, in the open omega, then this quantity is equal to 0, and this estimate says that U has to be 0 in M, so that it has to be 0 everywhere. And exactly, so now one can ask, okay, but I just said that this is the minimal time for which you have unique continuation. I said that this is the optimal result with respect to stability, because it is shown that you cannot have better than log. So our problem is solved. The problem is that the problem is not solved. And for me, it was interesting to study this because coming partially from control theory, I was thinking that this is a very complete result. And then I started working with Lowry and about the stability issues, and I realized, we realized that, in fact, the thing is that for boundary control, what one needs is unique continuation, not for any time t larger than the minimal time, but you really need to have the time t equal to the minimal time. And for those interested, or if you have seen something similar, I don't know, I can just say that from a technical point of view, this is really related to this orthogonality relationship. Like when I wrote this quantity here, essentially you want your G to be supported here, and this gives orthogonality between those two sets. So the way it translates to the unique continuation problem is that if you have a time t which is strictly larger than the minimal time, this will violate this orthogonality, will create a small overlap. And I think the best way to understand it is by a picture that I'm going to show. I'm just going to say that understanding unique continuation in the maximal domain, it's in fact the same as understanding how this constant here, c, blows up when t approaches the minimal time. And one way to see it is that you can just take a slightly smaller manifold. If you take a slightly smaller manifold, then you have this optimal time. So now this condition will be satisfied for the smaller manifold because the minimal time for the smaller manifold will be strictly smaller than the minimal time for the larger one. And then you want to investigate how this quantity will blow up as you approach the maximal domain, let's say. The best way to understand this is by looking at this picture. So how do we prove unique continuation in general? The main point is that in unique continuation, you work in a geometry where time and space are together. And you propagate the uniqueness, that is the set where your solution is zero, you propagate them in time and space. And what you do is that you use some hypersurfaces and you foliate and you prove uniqueness by following those hypersurfaces. And here, phi equal to 0 is exactly the wave cone. So this is exactly where the maximal domain where unique continuation holds. If you go after the characteristic cone, you don't have unique continuation. And this is exactly where unique continuation blows up. So saying that you fix a time t strictly larger than the minimal time is exactly the same as saying I fix some delta, some positive distance from the maximal domain, and I prove my unique continuation here. So this is exactly the same. This is how one should think of the problem. So when you say for time t strictly larger than the minimal time, I have this estimate, is like saying, okay, let's fix some distance delta from the maximal domain, which is the wave cone, and now I will prove unique continuation here. But the problem is that if you have a unique continuation result for any hypersurface which is as close as you want to the maximal domain, then you also have unique continuation up to the maximal domain. So in theory, you can also quantify this. But if you try to quantify this, the problem is that this will blow up, of course. And what you need to do is to have some explicit dependence and to understand how the blow up occurs with respect to delta, which is the distance to the optimal cone. So this is quite some technical work. So I will just say one sentence that with Lauri, we try to focus on some very particular case. So, okay, you don't need to look at this very carefully. It's just, we just take a ball of radius r in time r/2, and this is the optimal diamond. Here phi is an explicit foliating function, so it's exactly like this. It's a phi that will foliate and will reach the optimal cone. And what we did is that we were able to prove quantitative unique continuation with explicit dependence with respect to delta. And here the main point is that we have delta. Delta is the distance to the optimal domain, and we were able to show this exponential behavior on delta. Yeah, this is based on the technique is some Karleman estimates with this microlocal weight introduced by Tataru. And then we combine with the propagation ideas of Laurent Leouteau. And the main point is that, as it turns out, this estimate has to be iterated. And in each step that you iterate, you gain some uniqueness. But this was what we learned by our analysis. Due to this microlocal weight, you cannot advance too much. And so this is what gives this exponential in the constant. And then you can use an optimization argument. And that's the one of the interesting results is that this is a unique continuation result, but you see here, you have no loss. So C is a cylinder where you observe, and now you prove your uniqueness, you control your solution up to the whole diamond, which is the maximal domain. And what happens here is that the solution, the stability from log. So if you stay away from your maximal domain, we already show that you have log stability and that this is optimal. So what we proved is that when you go to the maximal domain, in this particular case that we studied, the estimate becomes log-log. So I will just make a comment that it may seem bad, but we cannot know, we don't know if it's optimal. But it's interesting to compare with the elliptic case for those who are familiar with elliptic estimates. So when you have unique continuation for elliptic operators, and you are in a set that is compactly contained in some open set omega, you have Helder stability. But you can also wonder what happens if you want to go up to the whole domain. So what happens in the elliptic case is that you have a log stability. So that what I want to say is that I'm trying to make an analogy saying that in elliptic case, from Helder stability, when you are far away from the optimal of the maximal domain, you get a logarithmic stability in the whole domain. And what we proved for the wave is that from log stability, which is optimal, you go to log-log. So from this point of view, even though log-log may seem a bad stability, it could probably just mean that indeed that's it. Of course, this is not any proof or anything. It's just some intuition. And now going back to inverse problems, this can be used and prove and an explicit in a particular case can use to show that we have an exponential approximate cost of the approximate control. And going back to our abstract result, we can use it in the case of a half space to prove that for the inverse problem of recovering the potential, the stability is going to be log-log. So once again, log-log, it's not a very strong stability, but at the same time, there are indications that probably this problem is not so stable after all. But yes, that's all that I wanted to say, and thank you very much for your attention.
Thank you very much, Spyros. It was a very, very nice talk. Are there any questions or comments, please? Any further questions or comments, please?
Maybe I have a comment. As
Yes.
to me, there is an operator background of the boundary control method, which is triangular factorization of operators. And I think that to investigate stability in time optimal setup of the boundary control method, we need to teach, to learn, to investigate stability of such an operation, of this operation of the triangular factorization of positive operators. And it is very delicate, abstract problem of operator theory. And there are some ideas how to do it. And in one-dimensional case, everything works excellent. But in multidimensional case, the problem arises that if this factorized operator is not an isomorphism. This fact induces a lot of problems. However, I suspect that a kind of continuity at the level of weak or strong operator convergence does exist even in the time optimal setup. But sure, the colleagues which work with quantitative stability also should try to improve their results, because strong operator convergence and moreover weak operator convergence does not allow quantitative estimates, unfortunately. So I think that the subject of the talk is very, very interesting, and I would like to thank Spyridon for very clear and rich in content presentation of the approach, and wish him all the best and success. Katya, also thank you for your for information about the conference. The project of this conference is very prospective and very attractive. Thanks to everybody.
Thank you very much.
Thank you. Yeah. Thank you very much for your kind words and for this very interesting remark. I didn't know about this operator, but yeah, I should have a look maybe. Thanks a lot.
Thank you. Thank you so much. Thank you so much. Are there any other questions or comments, please? Okay, if not, thank you very much, Spiros, for the very wonderful talk. Thank you very much, everyone, for coming. Thank you so much.